Hello there. In this lesson, we're going to learn about hybridization. So hybrids you might be familiar with in other aspects of life, like a hybrid car, which is a combination of like electricity and gas, or hybrids in biology, which are combinations of purebred gene traits. But here what we're talking about is a hybridization of the energy of electron orbitals. So if you remember in our quantum theory, we learned about s orbitals as being a lower energy orbital. And then within the same shell, you might have p orbitals as well, which are a little higher energy. So what happens is when bonding occurs, that those orbitals can combine and you end up with a hybrid, which will be orbitals that are all the same amount of energy and not as high as the p, but not as low as the s, so somewhere in between. And this allows for greater stability of bonds between atoms. So what that looks like is not only are the energies going to be different from each other, but the shape of those orbitals, the probability plots that you get, will also be different. And one notable difference is that they're not symmetrical anymore. So this is an s orbital here, which had this nice spherical shape. And this is a p orbital here, which had this nice symmetrical figure eight or dumbbell shape. And let's say you have an electron here, and then you bump one up to here, and you want to make bonds with both of them. Well, what's going to happen is you're going to get a hybrid of each, and you will have a combination of s and p together to make these new orbitals, right? So then you'll have two orbitals of equal energy, but the shape of their probability orbital is not symmetrical, right? You end up with a big side and then a teeny little side on the other side of the nucleus. So if we have a nucleus here in the middle, most of the electron density is going to be on one side of the nucleus with a little wee bit on the other side. So what happens is these big blobs of electron density, because of their negative charge, obviously, they're going to move apart from each other, repel, and you'll get some predictable shapes. And so that's what we're going to look at, is those shapes. So the first of our shapes we're going to look at is the hybrid between an s and one p. So if we take an electron here, like in beryllium, and put another electron up in its p subshell, and we combine the two of those, and we get one s and one p hybrid, or hybridizing. These are the two sp blobs, right? Remember, we got one big one and then one little one. And so what's going to happen is, if the nucleus is in the middle there, where there's other little blob on the other side, is that the two big blobs are going to go as far from each other as they can, right? And so you end up with this sort of linear shape. This is another way of representing it here. So you get a linear shape between the two blobs of electrons, right? And so if you were bonding the beryllium, say, to two other chlorines, you'd have a chlorine on either side here, and this would be 180 degrees between them because those hybridized orbitals are not symmetrical and they're going to move far away from each other. Likewise with boron, if we take boron and we take its 3 electrons and we spread them out so that we can make 3 bonds, that means we're going to need 2 p orbitals along with the s, and so you call this an sp2 hybrid. And so you would have 3 orbitals that are all equivalent, and they'll all have a big blob and a little blob and then a big blob and then a little blob and a big blob and a little blob, and all the big blobs are going to move as far away from each other as they can, which gives you an angle of roughly 120 degrees. And so molecules like BCl3 will have a chlorine that will bond to each one of those hybrid orbitals, and we'll get into the bonding in a little bit. Moving right along, we have a hybrid between 1s and 3 p's. So this is a very common one. Good old carbon, of course, has those 4 valence electrons, and they can spread out between the s and the 3 p's, and you combine them and you get an sp3 hybrid. This time it's got 4 big blobs that are going to move as far away from each other as they can on either side of that nucleus, and so you're going to end up with 4 possibilities for bonds with other elements. Not sure why I had a gap there. Anyways, something like methane, you could have 4 hydrogens all bonded to each one of these hybridized orbitals, and you'll end up with a shape that looks kind of like a pyramid and has a bond angle of roughly 109.5 degrees between each bond. Now, our molecules that involve valence shell expansion also will take shapes that are the result of repulsion of electrons. And so once you have all those hybrids made, if you have 5 pairs of electrons all hybridized so that they all have the same energy, you'll get 3 around the middle here. If you can kind of imagine like a Mercedes-Benz symbol looking down from the top. And then 1 that goes up and 1 that goes down. So these are like 90 degrees to the center plane. And then the 3 around the center plane, those are all going to be 120 degrees from each other, right? So you got 90, 90, and 120 around the middle. And the last one we're looking at here is when you have 6 pairs of electrons and you have them all trying to get as far from each other as they can. And so this hybrid with 1s, 3 p's, and 2d orbitals all combined ends up producing 90 degrees in every direction. It doesn't matter which pair of electrons you look at, it's going to be 90 degrees to get to the next one nearby. So there you go, valence shell expansion and the hybrids. So the next thing to consider is how do the bonds then form? And so it depends on the type of orbitals that are being combined to make the bond, but there's basically 2 options. The first option is by overlapping an s orbital or a hybrid orbital. So all the hybrids we know are all kind of like squished dumbbells with a big blob on one side and a little blob on the other side, and we're going to kind of ignore the little blob, so we're just going to be considering the big blob part. So to start with, we'll look at what if it was 2 s orbitals like hydrogen here. So hydrogen, you got 2 h's, we got an h over here with an s orbital, h over here with another s orbital. And what we want to do is show how these 2 might share electrons. And it's pretty simple. What you end up with is the 2 will overlap and make 1 orbital that goes around both of the nuclei, and you call that a sigma bond. Sigma bond. It's got this symbol sigma that shows that for these type of bonds, the greatest electron density is directly in between these 2 nuclei. So it's hydrogen nuclei in the middle here. And so the bond between them will be lots of electron density right in between the 2 nuclei, and that's what holds them together. Now this also works when you are making bonds between hybrid orbitals. So this is oxygen. Oxygen ends up making an sp3 hybrid. And so it has 4 blobs of electrons. So 2 of those blobs are going to overlap with the s orbital for hydrogen. So we got a hydrogen here, we got an oxygen here, another hydrogen over here. And so these 2 blobs are going to overlap and make sigma orbital. And these 2 blobs are going to overlap and get another sigma orbital. So if we're going to represent it, maybe I'll choose a different color here. I'll go with blue. So we'll make a nice sigma orbital here. That'd be our single bond to that hydrogen. And this would be another sigma orbital here. And that'd be to the other hydrogen. So then you've got yourself 2 H's and an O in the middle. And both of these have sigma bonds holding the nuclei together. In order to show that in our orbital box diagram, you can see that oxygen with an sp3 hybrid would have 2 spots open for bonding with the hydrogen. And then so once bonded, those hybrid orbitals would then all be full. There's the one hydrogen, there's the other one. Great. Alrighty, so option number 2 for bonding is called a pi bond. So sigma bonds are what occurs directly between 2 nuclei, and pi bonds are what will occur if that position is already taken. So when you have a double or a triple bond, you're going to need pi bonds to make those extra bonds. The first bond is always going to be sigma. So our example here is going to be considering oxygen. And so when we bond the first oxygen to the other oxygen, we're going to end up with a sigma bond that will take up the spot directly between the nuclei. That's great. Now we got one bond between the oxygen. But we know that oxygen needs two bonds in order to be stable, right? If we do your Lewis structure here, you know that we need to bond it twice. So we got one there, we need another bond. So the second type of bond is not an overlap of hybrids or s orbitals. It is always going to be p orbitals that allow for this bonding. If you remember, p orbitals have the nice symmetrical two blob structure, or dumbbells, or whatever descriptor you want to use for it. It's got two areas of electron density. And what happens is both those areas sort of merge. And so this top two blobs, they're going to merge to make one half of a pi bond. And these bottom two blobs, they're going to merge to make the other half of the pi bond. Maybe I need a different color for this, so we'll use green this time for the pi bond. So there you've got one half of the pi bond, there's the other half of the pi bond. So that's great. So back here with our oxygen, because the sigma location is taken up, you can add a pi bond on top and below. I kind of think of it like a hot dog bun, where the sigma bond is like the wiener, and then the hot dog bun goes on top and below, and that represents a pi bond. And just like with a p orbital, it has two blobs, a pi bond also has two blobs. So two blobs, still one bond. And so this is a double bond between two oxygens. If there's an oxygen on this side, an oxygen on this side, you have the sigma bond holding the two oxygens together, and you have this pi bond doing the same thing. So one sigma and one pi bond, making two total. Alrighty, so let's illustrate to show how this looks all together. We know that C2H4, if you're going to bond two carbons and you're only going to have 4 hydrogens to do it, then you're going to need a double bond in order to make that happen. So something like this, if you're making your Lewis structure and you're like, aha, there's 2 bonds. So that means we're going to have to do the same thing that we did with oxygen. So let's illustrate here. I think we went with blue for sigma. So we know that the first bond between any 2 atoms is always going to be sigma, right? Sigma there, sigma here, sigma here, sigma here, and sigma here. Great. All the single bonds are going to be sigma, and the first bond for any multiple bond is also going to be sigma. And then to make the second bond, it's going to be an overlap of p orbitals, and that is going to be our pi bond, and that is the second bond that holds these two together, right? So remember, 2 blobs, 1 bond for the pi. Now for our C2H2 here, that's going to be a triple bond between the 2 carbons, and then the 2 hydrogens attached at either end. So again, let's draw it out. We have a sigma between the 2 carbons, and we got a sigma between the carbon and the hydrogen, and a sigma between the carbon and the hydrogen. And then we got to add in these pi bonds. So the second bond here is going to be a pi bond, acts like a sandwich. So that's 1 pi bond. And then you have to imagine sort of 3-dimensionally to get that third pi bond, or second pi bond, which is the third bond between the 2 on there. So you can imagine one that's out in front here. I'm going to shade it dark. That's the second pi bond on the front. It's closer to you. And then you got to imagine another one in there behind the sigma. There it is. That'd be the back one, right? There we go. So you have to use a little bit of your 3D imagination in order to visualize where all of these pi bonds can exist, right? So you got a sigma in the middle, a hot dog bun on the top and the bottom, and a second hot dog bun going front and back to hold those 2 carbons together. So now that you know all these options, it's pretty easy to work out the hybridization for any molecule. Now we're only going to be considering the central atom, just the atom that's in the middle of these molecules, but you can do it for anyone. Remember that the only hybrids are going to be the first bond, right? The sigma bonds are the only ones that are possible to make with a hybrid. And so it's pretty easy to work out the hybridization if you just add up all the bonds along with any lone pairs that there might be. So lone pairs are hybrids, and you get one hybrid for each bond, whether single, double, or triple. So for our first one here, looking at the carbon, you can see we have a bond here and a bond here, so that means an S and a P will do. That's 2 bonds, that's all the hybridization you need. Here we got 1, 2, 3, so that's an S and 2 P's, that makes 3 to get the hybridization for that one. Here we have 1, 2, 3, and a lone pair here, so that is an sp3 hybrid, because you need 4 bonds total, or 4 hybrid orbitals total, not bonds. 3 of them are bonds. And the last one here, we got sf4. We've got 1, 2, 3, 4 bonds and 1 lone pair. So that means S, 3 P's, and a D, which will make 5. All right, hope that helps. We'll see you soon.